So although we spend a lot of time practicing those lovely linear equations, y equals mx plus b, that are a perfect straight line, in the real world, when we're collecting data, it is so rare that you would actually see things in a perfect straight line. So I have this little scatter plot for us. Unfortunately, it's not real data, but it is going to be for us to play with for now. So if we're trying to describe the pattern that we see in this data, we are going to try to find a line that approximately describes the pattern we're seeing here. It's not going to be perfect. There's going to be error in it for sure, but we can make a line of best fit. And then a line of best fit is going to give us this approximate model of how these two variables are connected. So for us, we're going to be doing linear models. There's also quadratic, exponential, logarithmic models, but for us, we're just looking at linear. And it's called line of best fit or the least squares regression line. You'll learn more about it in your stats class, but essentially, this line of best fit is minimizing the error we have from all of the points. Because so although there's many ways I can draw a line that I think best represents this data, if I draw one maybe here, that might look like a small amount of error for these points here, but a very large amount of error for these ones here. They're very far from this predicted value. So when I'm drawing my line of best fit, I'm just trying to kind of capture this pattern and be as best as I can in the middle. This is easier and harder depending on how spread out your data is. But we're going to pretend it's that for now. In this class, what we're really going to do is use technology to find our line of best fit. But first, let's look at my little estimate one. We are going to see the expected value when x is 6, and then saying, if this data would keep continuing in the same pattern over time, could we also guess what our value might be when x is 12? So when x is 6, I've got like, I don't know, maybe 9.7. Why not? And when x is 12, it looks like just over 15, maybe say 0.2. And those are just my best guesses. But notice these are my expected, but we do have an actual value at x equals 6. Our actual was 611. So we can already see that error in between my actual and my expected. You also really have to be careful when you are extrapolating. So we're going outside of this data range that we have. So if I'm assuming it keeps going forever and picking a number like 12 or like 15, that can bring in some really complicated assumptions. So you are always safer looking at expected values inside the data range you have than saying, oh, I bet this will continue forever, because there are many cases in which that isn't the case. And we have these upper limits on data values. So I am going to I saved this table for us. So I'm going to open it up in Desmos. If you're following along at home, you can feel free to scan this QR code and do it on your device. I'm going to click on this link and I will make sure the link is in the description if you'd like it there. So here we are with that data set. And I have it already in a table for you. But you can, if you're just given data in a table, not already beautifully put into Desmos for you, you can come to Desmos, click Add Item, and go to Table. And then it'll let you type in your data and it'll graph it for you automatically. And then you can do your least squares regression line like we're going to do right now. So here's our data. Remember, I had that sort of estimate line around here somewhere. And now we're going to have Desmos do it for us. So I have an X1 and a Y1 in my table. And what I'm going to do is write essentially y equals mx plus b, but without that equals, because I am asking Desmos to do my approximate best fit line. So I'm going to write y sub 1, and that sub I'm using the underscore. And instead of equals, I'm going to do the little approximately m times x sub 1 plus b. And then Desmos automatically finds my parameters for me. It finds that slope and that y-intercept that give me my line of best fit. These parts here are going to be helpful for you when you're in your statistics course. We're not very worried about them now. So let's head back and make some comparisons with what we estimated and then what Desmos actually calculated for us. So using that M and B that Desmos gave us, the line of best fit was about 7776 times x plus 5.1538. I'm using 4 decimal places. It's really up to you. Now we can plug in these values to see what these truly were using the correct line of best fit rather than my messy little estimate. So when we plug in 6 to this equation, we're going to get out 9.822. And when we plug in 12, we're going to get out 14.49. So really, honestly, we have pretty good estimates, but Desmos or other technology like Excel is going to give you that perfect line of best fit that minimizes your errors. And I was pretty lucky with that line there. I am not always so lucky. So this is just a description of what we just did in Desmos. Here is the equation you are going to put in to have it calculate that regression line. And these are the keys that I used to type y sub 1 and then x sub 1. That's that underscore key. It will give you m and b, and then you will have that line of best fit.